All right, we got numbers 3 and 4, our third and fourth parent functions here that we're going to look at. And these have fancier names, quadratic and cubic. Okay, you should have learned about quadratic equations in Algebra 1 as well. Quadratic equations, okay, they all have the highest exponent on an x is a 2. Okay, so quadratic equations all have an x squared in it. Okay, so again, thinking about what that would look like, if I just picked my standard 5x values, what would happen if I substituted these in for x here, right? Because I'm performing x squared. I'm squaring all of these numbers, right? Which again, squaring means that number times itself. So if I do -2 in here, -2 squared, or -2 times -2, would be +4. -1 squared, so -1 times -1, +1. 0 squared is 0. There's my origin point. 1 squared, or 1 times 1 is 1. And 2 squared, 2 times 2 is 4. Okay, so you see that it's similar to the absolute value graph in that it kind of starts higher, it goes down to 0, and then it comes back up. Okay, and it's true, it does look pretty similar to the absolute value graph. Okay, but it's going to be a little bit different. So look, -2 comma 4, -2 4 up here, -1 1, 0 0, 1 1, and 2 4. So you may remember that this graph is called a parabola. Okay, it's kind of this U-shaped, kind of comes down, hits a vertex, and then comes back up. So it is similar to an absolute value, but an absolute value is very much so a V, and it's kind of like straight lines going out from the vertex of that. Whereas this one, they're definitely more curves, right? So this quadratic is more of a U shape, whereas the absolute value is a V shape, okay? So then again, thinking of the domain and range here, you probably heard me explain this in the domain and range video as well. But again, the question is for the domain. We're asking, does it extend forever to the left and to the right? And it doesn't look like it will, but again, Desmos is helpful. If you would type this into Desmos and zoomed out a whole bunch, you would see that, yeah, the x values do keep getting bigger and bigger, which means it will not stop. It will not stop expanding from left to right, which means the domain is all real numbers here. Okay, and then similarly to absolute value 2 for the range, right? Same thing. It does not go down forever, but it does go up forever. Okay, and for that, right, we would say, okay, the y values, right, the lowest it ever gets on the y-axis is 0, but then it hits every y value above that. So for that range, we would say y is greater than or equal to 0. All right, so that's the basics of the quadratic parent function. Okay. Now cubic, okay, the cubic, you might not be familiar. We're not talking this kind of cube here. We're talking cubic. That's the word for x to the third power. Okay. So the standard equation would be similar to quadratic, but it would be y equals x to the third power. Okay. So when we think about this, right, if we pick our same standard x values, okay, what we want to do here is plug those in same way, okay. But cube, right, to the third power means, right, multiplying 3 of those by itself, right? So like -2 times -2 times -2 would be how I would get the y value that goes with that, okay? So -2 times -2 times -2 would actually be -8, okay? You could do that in a calculator, but yeah, that ends up being -8. -1 times -1 times -1, or -1 cubed, would be -1. It would actually go back to a negative. 0 cubed is still 0, right? That origin point. 1 cubed, or 1 times 1 times 1, is still 1. And then 2 cubed, or 2 times 2 times 2, is 8. Okay, so you see a pattern with a lot of these parent functions with what the y values end up being. A lot of the time it is kind of like a mirror image, like these, or right, the negative x values result in negative y values, and vice versa. Okay, that happens. Okay, but the big thing that you're trying to do here is just kind of get a feel for what these graphs look like, and associating the shape of the graph with the equation and the name of the function. That's our big goal for these. Okay. So again, looking at my x and y axis here, okay, so x is -2, y is -8, all the way down here, -1 comma -1, 0 0, 1 1, and 2 8 up here. Okay, so what's this going to look like? Well, if I connect those, we see that it is more of like kind of like a curvy like S not like quite like an S, but like this kind of flattens out for a bit and then starts going back up again, okay? So that's what a cubic graph looks like, okay? And it'll keep extending those directions forever, going up and down, okay? So thinking about the domain and range here, right? Again, same questions. For the domain, we're asking, does it extend left and right forever, okay? And again, same thing with quadratic, where like it doesn't look like it would keep going to the left and right forever, but as this curve keeps getting wider and wider, it does. And the same applies here, where it looks like this would straighten out eventually, but again, if you zoomed out and zoomed out, it does very gradually end up going wider and wider on the x with your x values. So yes, this domain is all real numbers as well, even though you might not think it. And then the range, okay, easier to see. Does it extend up and down forever? And these arrows imply that yes, it does. So that would also be all real numbers. So that is that cubic graph, what that looks like, okay? So those four, we got 4 out of 6 done, so I just got 2 more. Let me erase, and we will introduce you to those as well. Thanks for staying with me so far. We got numbers 5 and 6 here, square root and cube root. So let's jump into these. Okay, the square root. Okay, so as you can imagine, for this one, the equation would just be y equals the square root of x, right? So taking the square root, we're looking for like what times itself would equal that number in the radical, or that's called the radicand. And then we'll find all the same information with these, okay? But what's interesting with these, right, if we would go to pick my x values to plug in here, okay, we're more limited because can you take the square root of a negative, right? If I'm wondering, like, what times itself equals -4? No, there's no whole number that would equal, or there's no even real number that would equal the square root of a negative number, okay, because nothing times itself equals -4, okay? We'll actually talk about that later in the year. Yes, so we have to be more selective, okay? So look which values I'm going to pick. 0, 1, 4, 9, 16. Do you know why I would pick those? I would pick these because these are numbers that are called perfect squares, meaning if I took the square root of these, I would get whole number answers, okay? If you don't know what I mean by that, look at this, okay? So if I put in 0 in here, what's the square root of 0? Or what times itself equals 0? 0, yeah, 0 times 0 is 0. And like I said, the origin is going to be included with all these parent functions, okay? Now 1, if I plugged in 1 in there, okay? Square root of 1, or what times itself equals 1, that would be 1, okay? But look, 4, if I took square root of 4, what times itself equals 4, that answer would be 2, right? Because 2 times 2 equals 4, so the square root of 4 is 2. Now 9, right? The square root of 9 would be 3, because 3 times 3 is 9. And then 16, okay, square root of 16 is 4. Okay, so you can see why I picked the numbers that I did for my x values, because, 0, 1, 2, 3, 4, these are the first 5 perfect squares, okay? So then plotting these points on my graph, okay, I'm not going to be able to get this one because that's going to be too far away, but okay, it's going to be different, a lot different shape than the other ones. Okay, I'm starting at my origin, and then 1, 1, 4, 2 would be all the way out here. 9, 3 would be all the way out here. Okay, so this graph is not quite right, but that's all right. This graph is kind of just, it starts at the origin. It's almost like a cannonball shooting off, right? It's just shooting out to the side here. So that is what that graph looks like of a square root, okay? Different than the other ones. Okay, but then thinking for the domain and range here too, this is going to be different, okay? Because the question we're asking is, does this extend forever to the right and to the left? Okay, that's for my domain. No, it does not, okay? It does not extend to the left forever, okay? We see this arrow, meaning it's going to go to the right forever, but does not go to the left. So that would mean that this domain is x is greater than or equal to 0. Right? Because it does not go into the negatives for the x. And then the same for the range, right? Does it extend up and down forever? No, okay, no, it does not. Definitely doesn't go down forever. And then this graph, yeah, will eventually keep creeping higher and higher for my y values. So it does extend up. It will go up to positive infinity eventually, but does never hit the negatives. So the range would also be y greater than or equal to 0, okay? So that's the square root graph, a little bit different than the other ones we've done. Last one, cube root, okay? Cube root is just the opposite of cubing something, right? Cubing is taking it to the third power. Cube root is kind of wondering what times itself equals the number in the cube root, okay? So this one's going to be different as well. Look at the x values that I'm going to choose here when I get points. Okay, I'm going to choose -8, -1, 0, 1, and 8. And if you're somebody who's very observant, you might notice that, oh, those were the y values that I had for my normal cubic function, okay? And that's true, okay? So you're going to see what happens here. If I substitute this in here, right? So if I think the cube root of 8 or -8, okay, you might be saying, oh, you can't take the radical of a negative. With cube roots, you can, okay, because something times itself can equal a negative, okay? The cube root of -8 ends up equaling -2, right? Because we said with cubic, -2 times -2 times -2 equaled -8, okay? So yeah, the cube root of -8 is -2. So it's taking the cube root is just the opposite of cubing, or taking it to the third power, okay? So that would mean that, yeah, if I took the cube root of -1, I would get -1. Cube root of 0 is 0. 1 is 1. And the cube root of 8 is 2, okay? So you can see it's just the very exact like inverse of the cubic function, okay? And that's helpful to remember too. And so you're going to see those graphs, the cubic, right? Remember, cubic graph looked like this, where the cube root, look how this is going to look, okay? If I graph these, -8, -2 down here, -1, -1 right here, 0, 0, 1, 1, and 8, 2. So we go up through the origin and then looping back, okay? So notice, normal cubic graph looks like this. Cube root is just kind of like that turned on its side, okay, or the inverse of that. And again, that's because the x and y values are kind of flipped around, okay? And then thinking about the domain and range here, just doing this real quick. Does it extend left and right forever? Absolutely, so that's all real numbers. And then similar to what I said about other graphs, even though it doesn't look like it, this will eventually creep up and down forever in both directions. So the range is also all real numbers. And I forgot to draw my shape for my square root here. The square root shape is looking like that, okay? So those are the 6 parent functions. I know that's a lot. I know that's a lot to absorb. Okay, I'm hoping too you can use this video down the road, kind of refer back to it if you ever forget these things. But it's helpful that we start here, that I introduce you to all these, just what the general shapes of these graphs looks like, because what we're going to do is we are going to use these to help us to know what is happening when I shift these graphs around, okay? And so that's what the rest of the unit's going to be about, okay? So thanks for following. So we're going to start with transformations in the next video, so stay tuned.